Welcome to this lecture series in real analysis. In this lecture, we'll look at some important properties of convergent sequences, and let us start by recalling what we need. So just give me 1 second. Yeah. So we will need the notion of null sequences. Recall that a sequence is called null if its limit exists and is the point 0, the number 0. Okay. Also recall that we established this very simple connection that if we have a sequence whose limit is x, then one can form this sequence whose nth term is the difference between the nth term of the original sequence and the limit point. Then this sequence is null, and conversely. So this happens if and only if that happens. Okay, and we saw a very simple property that, or fact, that if we have a null sequence and a bounded sequence, then this sequence, whose nth term is the product of the nth terms of the two original sequences, is also a null sequence. So these are some of the things that we will use. All right. Here are some problems for practice. And now let us get started. So first we will prove a very basic fact that every convergent sequence is a bounded sequence. So this should be intuitively clear. Suppose we have a sequence and let's say it converges to some point x. Then we know that beyond some large enough time, all the entries of the sequence lie in a chosen interval around x. So after a certain large capital N, all the xn's, meaning whenever little n is exceeding capital N, all of them are controlled, meaning they lie in a finite region. And before that, you only have finitely many entries in the sequence. So if you just take the maximum of the magnitude of the things here and the things which preceded them in time, that would be a uniform upper bound to the magnitudes of all the elements of the sequence. So let us just write all of this in detail. This is the idea, but let us just write it down. So let xn be a convergent sequence and say it converges to x. All right. Want to show that the sequence is bounded. So we know that by definition of convergence, we know in particular, in fact, that this happens ultimately no matter what positive real number we fit in place of epsilon. So a most convenient choice is 1, so we use 1. So this is just a very special consequence of this equality. Right, so we have this. And therefore, just unraveling the statement, such that whenever little n is at least capital N, we have this happens. So we have just unraveled this statement. And therefore, whenever little n is at least capital N, we have this is the case. Now, why is this the case? Well, you can use the triangle inequality. So first, from here, you move to, let me make an imply sign. Right, so all I'm saying is that this implies that, in fact, they are equivalent. And now on the left-hand side, you use triangle inequality to say that this thing is dominating that thing. Right, and that's it. So, you don't really need to know triangle inequality to establish this. You can just use your common sense, but that is one way to immediately see it. So beyond this large time, we can control the size of xn by this uniform quantity. And therefore, immediately we have this thing is controlled. Let me use a different color because this is the end. So therefore we have, this is less than maximum of this quantity. So this takes care of whenever little n is at least capital N. And to take care of the rest, we may just write the rest. Right? This is true for all n. And now this is just one big number, which is taking care of the magnitude of all of the xn's, and therefore the sequence is bounded. It's a very simple statement, but we did the proof in full detail. All right. Now for the interesting part, it's unrelated to the previous one. Suppose we have two convergent sequences. Then the limit of the sum of the two sequences, so when we say the sum of the two sequences, we mean a sequence whose nth term is the sum of the nth terms of the original sequences. So what we are saying is that if we are given two convergent sequences, then the limit of the sum sequence is the sum of the limits of the original sequences. So it in particular says that the sum sequence converges, and in fact, the limit of the sum sequence is the sum of the limits. So you may think of it as the limit kind of getting distributed inside this bracket. Okay, so this is kind of an algebraic property. Similarly, if you scale a sequence, so fix some real number c, and scale every entry of the sequence, you obtain another sequence. You may call it the scaled sequence. Then the limit of the scaled sequence is the scale of the limit. Right? Very nice. And similarly, if you product two sequences, meaning if you take a sequence with nth term is the product of the nth terms of two sequences, if they are convergent, then the limit of this product sequence exists and is equal to the product of limits. So the limit kind of again gets distributed in this product. So very nice properties, and let us prove them. So here is the first one. Okay. So first of all, say this limit is x, and this limit is y, and we will refer to both of these simultaneously by star. Okay. So now fix an epsilon greater than 0. Yeah, before we do that, so define Zn as this thing. And what we want to show is this is exactly what the problem, or rather the first one, is stating. We have just recast the problem in different symbols. So fix epsilon greater than 0. Our goal is to show that. That this inequality happens ultimately over n. That's exactly what it means to say this happens. This means that for all epsilon, this happens ultimately. So if you fix an epsilon arbitrarily and show that this happens, then you have established this equality. Right, so now this will be the goal. And now by star, we have, by star, and in fact, I'm just looking at this for the moment, we have epsilon by 2, I will write. This happens ultimately. Right, again, what does this mean? This means no matter what delta you choose, this will, whatever positive delta you choose, this will happen ultimately. So we choose epsilon by 2. You will see why we have chosen epsilon by 2. And we also have, now we are looking at the other part. and we have ultimately. Right? And now I will write another statement which may look a restatement of the previous one, but it is not. So therefore we have ultimately. Now this may look like a restatement of these two statements, but it is different, even though the deduction is trivial. What the first one is saying is that there is some large enough capital N such that whenever little n is at least capital N, this happens. The other one says that there is some large enough capital N prime such that whenever little n is at least n prime, we have this happens. But if you just choose the bigger of the two ones, bigger of the two meaning bigger of n and n prime, then whenever n is at least that bigger number, both of them happen. And that is what we are saying here. So there is a single big number, call it m, such that whenever little n is at least m, both of them happen simultaneously. Okay? And now since both of them happen, ultimately, we get the sum is less than epsilon by 2 plus epsilon by 2 ultimately. Right? If this happens ultimately and that happens ultimately, we just sum the two inequalities. That will also happen ultimately. But now by triangle inequality, what is this? This is at least... so this is at least xn plus yn minus x plus y. Right? We are using triangle inequality. Yep. So we have that, but that is Zn. So that implies mod Zn minus x plus y is less than epsilon ultimately. And that is what was our goal. This was the goal. So make sure that you follow all these steps thoroughly. This is the kind of reasoning that will appear over and over again throughout the course. Okay, so we have established this first thing. The second part is an exercise. So this is an exercise. It's much simpler than the first one. And let me prove the third one. You can prove the third one on these lines, a very kind of a first principles approach. But let us invoke what we proved about null sequences, what we recalled in the beginning of this lecture to smoothly do this. Okay, so to prove 3, suffices to show that. So again, what we are doing is we have x is the limit of the first sequence and y is the limit of the second sequence. So suffices to show, suffices, or you could say equivalent to show, that this sequence is a null sequence. Right? This is exactly what we need to do. Because once you show this is a null sequence, it just means that this thing converges to that thing, and that finishes the proof. So why is this a null sequence? Just observe. So observe that xn yn minus xy is this times xn plus this times y. So we have just written this sequence as a sum of two different sequences. As you run over little n, this generates a sequence, and so does this. So the nth term of this sequence is now the nth term of two other sequences. All right. Note that this is a null sequence. Yn minus y is a null sequence. Okay. Xn is a convergent sequence and hence a bounded sequence. We just showed that convergent sequences are bounded. It's a bounded sequence. And now what we recalled was, if you have a null sequence multiplied with a bounded sequence, you get a null sequence. So this is a null sequence. Okay, the first one is a null sequence. Now here, this is a null sequence because xn converges to x. This is the null sequence. And well, this is just a constant sequence. You can think of this as the constant sequence y, 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 y. For each n, this term, or you can think of it as okay, so let's not do it that way. So you have this sequence, which is the null sequence, and this you can think of as the scaled sequence. This sequence has been scaled by a number y. And now by second part, which we left as an exercise, if you scale a null sequence by y, you again get a null sequence because the limit of this is y times the limit of that, but the limit of this is 0 because this is a null sequence. So this thing is also a null sequence. Okay, so we have a null sequence plus a null sequence, and now by the first part of this theorem, which we have proved, we see that this is a null sequence. And that's it. We wanted to show this is a null sequence, but we broke it as the sum of two null sequences, and hence we do indeed see that this is a null sequence, and that's it. So that proves that this thing converges to that. So this is a slick way of doing it, but you can do it in a more basic first principles approach also. Okay, let's move on. So now we have, we took care of addition, scaling, and multiplication, but now we go to division. So we have a sequence of real numbers such that three properties are satisfied. First of all, it is convergent. Second is that none of its terms are 0. And the third is that its limit is non-zero. Under these three conditions, we will show that this inverted sequence, meaning whose nth term is the inverse of the nth term of the original sequence, is also convergent, and further nice algebraic things happen. Limit of the inverted thing is inversion of the limit. So this is what we will prove. And before we begin with the proof will be very short, but before we begin with it, here is a small exercise for you. That these three conditions imply that the inverted sequence is a bounded sequence. Okay, this is a very important exercise since this course is your first introduction to probably to higher mathematics and certainly to analysis. Solving such exercises is what builds muscle towards understanding, to chunking the main core aspects of analysis. I mean, this is just it's a simple exercise, but it is important that one does it. Okay, so I'll assume that you have proven that this inverted sequence is a bounded sequence. And now to prove this, again, we will use our null sequences approach. So say this limit is x, and then suffices to show or is equivalent to show this is a null sequence. Because once we do it, we will have established that the limit of this exists and is equal to that, which is that number. So we will show that this is a null sequence, but that's very clear because this expression is nothing but this. And before we continue, note that why is this even a legitimate sequence of real numbers? First of all, since none of the xn's are 0, 1 upon xn is a legitimate real number, and hence this is a real sequence. Now, since the limit is assumed to be non-zero, this is a legitimate real number. And of course, somewhere we will need convergence. Without that, there is certainly no way to, it is not going to be true that in general this will be convergent. It may become convergent even for non-convergent xn's, but For generality, you need convergence. In fact, you need all three conditions to make this statement. Anyway, so we have written that this is equal to that, and the denominator is again non-zero, so this is a meaningful expression. And let us write it like this. Okay. Now this is a null sequence. Well, when I say this is a null sequence, this is the nth term of a null sequence. I'm just being a little loose like I was in the previous proof. So this is a null sequence. And by this exercise, 1 by xn was a bounded sequence. And now if you scale a bounded sequence by a non-zero, by any real number, you again get a bounded sequence. So this is a bounded sequence. And as we saw, if you have a null sequence produced with a bounded sequence, you get a null sequence. So this is a null sequence, and that finishes the proof. So this null sequence trick is actually very useful. In the previous lecture, it may have seemed like an artifact. Okay, so far so good. Let us continue. So now this is a very simple one, but a very important one. Start with a convergent sequence. Then every subsequence of this convergent sequence also converges and converges to the same limit as the original one. So subsequences of convergent sequences converge. Further, they converge to the same limit. Again, this shouldn't be intuitively challenging because, roughly speaking, what are you doing? When you have a subsequence, you're kind of throwing away some time instances. So you had some sequence which ended up converging to, let's say, some point x. So after a certain point, they kind of home in on x. But if you are taking a subsequence, you are dropping some of the entries along the way and reaching faster. If anything, you're reaching faster to your limit. So a subsequence converges to your limit, quote unquote, faster. We haven't discussed anything about rate of convergence, but this is not just true, this is very, very true, if that makes sense. So let's prove this. So let me change notation a little bit. So say limit, I'll say I going to infinity xi is x. Here the dummy index was little n, but I switched to I. And now let this be a chain of natural numbers of this sort. And therefore we thus get a subsequence. Right? So we get a subsequence, and what we want to show that the subsequence converges and has the same limit as the original one. This is what we want to show. But so to do this, fix epsilon greater than 0. And now by this fact, again call it star. By star, we have this is less than epsilon ultimately. Okay, we have that. But if or let me just say therefore, this also happens ultimately. Now, technically one should do this very, very formally, and one can do it. But let me just say in words. In fact, I will be kind of repeating what I said towards the intuitive idea of this proof. This happens ultimately, meaning there is some large enough large enough capital N such that whenever I is at least capital N, this happens. Okay. But whenever I is at least capital N, so is Ni, because Ni is at least I. These are all strict inequalities. So basically at the heart of this proof is the fact, very simple fact, that Ni is at least I. So if I is at least capital N, Ni is also at least capital N, and therefore this implies that. That is the main idea. That is, if you can convince yourself of that, that is it. Okay, so subsequences of convergent sequences convergent, they converge to the same limit. Finally, we can just write a simple corollary whose proof is already here. Fix a sequence in R, then these two statements are equivalent. The first is that the sequence is convergent, and the second is that every subsequence is convergent. We are not saying that it converges to the same limit or anything. We are just saying every subsequence is convergent. So 1 implies 2 is already done in the previous page. And the fact that 2 implies 1 is a tautology because xn itself is a subsequence of xn. So I don't know if this corollary helps at all, but yeah, it is there for us to look at. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.